I'm going to start with 1-bit gates. Sounds pretty boring. If we look at classical computers, there's only two 1-bit gates. One is a buffer. Put in a 1, you get out a 1. Put in a 0, you get out a 0. Then there's a NOT gate, which means you put in a 1, you get out a 0. Put in a 0, you get out a 1. How many 1-bit gates are there in quantum computing? There's too many to mention. In fact, there's an infinite number of 1-bit gates that you could come up with, but we're only going to consider a few of them. Here's my buffer. You put in a 1, you get out a 1. Now, is that obvious from this? Maybe not. Let's put a vector over here, a 1, 0, which is the 0 state vector, and multiply it times this. Okay, 1, 0 times 1, 0 gives you a 1 in the first spot, and a 0, 1 times 1, 0, which gives you a 0 in the bottom spot. So that makes it a buffer. Let's test the other case just for the heck of it. Let's put a 0, 1 here. Then the first row times the column would give us a 0. 1 matches up with 0, 0 matches up with 1, so that gives us a 0 in the top, and a 0, 1 times a 0, 1, that just gives us a 1 down here. So that's a simple buffer. I for identity. X is the NOT gate, or the bit flip. So if we put a 1, 0 here, the 1, 0 would give us a 0 in the top spot, and 1, 0, 1, 0 times the vector 1, 0 gives us a 1 down here in the bottom spot. So a 1, 0 becomes a 0, 1. In the same way, if we have a 0, 1 here, the top spot, 0, 1 times 0, 1, that gives us a 1 in the top spot and a 0 in the bottom spot. So this flips the bit. That should be it. From classical computing, that's all you got, is a 1 comes in and the same thing comes out, or a 1 comes in and the opposite thing comes out. But look at this. The states of the single bit, or the single qubit, want to emphasize single qubit, can be all kinds of states. Remember, it can be a superposition of states between 0 and 1. So let's look at this gate right here, and I'll look at the little phrase that comes with us, bit and phase flip. Bit and phase flip. So let's see what happens here to this. If we put a 1, 0 here, then the top spot is going to be a 0, and the bottom spot is going to be an I. What's I? I squared equals -1. So that's the imaginary state, and that affects the relative phase between the two. And if we put a 0, 1 in here, then that comes up to be a -I over 0. Put in a 0 and you get a 0I. You put in a 0, 1, you get a -I over 0. So it flips both of them. Is there anything that just flips the phase? The 1, 0 just gives us a 1, 0. No big deal. I don't see a phase difference. If you put a 0, 1 in here, you get out a 0, -1. So because of that negative sign, that gives us a phase flip of 180 degrees. Hadamard gate. We'll understand what this 1 over square root of 2 is when we realize that the probabilities have to add up to 1. 1, 0 gives us a 1 in the top and a 1 in the bottom. So that's going to be half of 1 plus half of 1. So that comes up to be a 1 when you add the two together. 0, 1 applied to this, you're going to have a 1 in the top and a -1 in the bottom. So essentially it's going to be these two states added together if it's a 1, 0, and they're going to be, the two states are going to be subtracted. This is the main diagonal, so it's going to keep things pretty much the same, but look at what these indications are. Square root of z, well, let's see what z is. Okay, the square root of -1 is definitely I, so that matches up with this one. Square root of the S gate, well, we just got from that, and you take the square root of I, e to the I pi over 4 power. It gets worse and worse and worse and more complicated where you have rotations. Now, you can test this, but this does satisfy the property of a unitary gate, because if you add up the squares of these things, you're going to end up with 1. This is a short video, but it shows a building block of 1-bit gates and how rich the choices are with quantum gates. And once we get this established in your brain, which this video is supposed to do, then we can go on to 2-bit gates, and then 3-bit gates, and then we can build circuits from all of these things. So let's just use this as a baby step towards building circuits.